Well, we have solved for shear and moment at a point. And I suppose there's a variety of reasons why one might do that. If we suspect there's a weak spot or repair at a particular point, or if there's just some point where it is critical that you want to analyze. However, the general case is when we want to have equations that define shear and moment for the entire beam. And when we do that, we might be able to graph them, because if you have an equation, you should be able to graph it. And obviously, if there's a graph, there's probably an equation that was used to describe or to create that graph. But once we have a graph, we can look for the maximums, and that's really where the power is of shear and moment equations and diagrams, because if we look for the maximum moment or the maximum shear, that would be the obvious place where we would do some additional investigation or some additional design analysis. So again, here's a fairly simply supported beam. Here are the shear and moment diagrams. What you can see is that there are places where this diagram takes different shapes. Those shapes changes occur where there are discontinuities. And we're going to talk about those, but basically wherever there's an applied force or a reaction, there's going to be a change, a sudden change in the shear, which means that it is a discontinuity. Wherever there's an applied moment, there will be a discontinuity in the moment graph. You don't see that in these two pictures. But what it basically says is that because there is no continuous graph, there is no single equation that defines this graph. So therefore, you need several equations. In fact, in this case, you need 3 different equations to define the whole thing. And over here, you'd need 3 different moment equations to define the whole beam. So what we're going to do is we're going to remember the positive shear and moment conventions, which we have here. We're going to remember, or we're going to observe, that there are discontinuities of shear and moment that occur at transitions and loads where there's changes in supports or loads. Unique equations need to be written for each equation between those discontinuities, and those equations can be graphed into shear and moment diagrams, which we'll try to do here. Positive is above the x-axis and negative is below the x-axis for both of these situations, or for both of these graphs. And there's some good tools in the book. You should look carefully at the steps to get there, the procedures for analysis. These are, I will use them. I'm not going to dwell on them as much. I think you should look at those in the book and be familiar with them. All right, so let's write the shear moment equations for this beam. First of all, let's find the reactions. All right, so there's a 5 kilonewton force down. You would expect that there's an AY and a CY. Because this is a symmetric beam, I think you can pretty much guess that AY is equal to 2.5 kilonewtons and CY is equal to 2.5 kilonewtons. All right, without doing a lot of analysis, I think we can just observe that. What we want to do is find the shear and moment that happens between the discontinuities. There's going to be a discontinuity that happens right here. So I need to define the shear and moment that happens between A and B. And I'm going to draw a little section like that. And so let's just draw the free body diagram of that section. And I usually put a little squiggly on there, just saying that that is the section. There's an AY. And there are no other forces applied here, so I'm just going to put the shear and the moment. This is actually going to be as a function of x going from some point, and I'll call it the reference point there. To find out the shear, we do sum of the forces in the y is equal to 0. So I have AY minus shear is equal to 0. So shear here is equal to 2.5 kilonewtons. It's positive in the direction that I drew my arrow, so that's good. What's the moment? We do some of the moments about any point, and I'm going to do some of the moments about A is equal to 0. Again, it's always in equilibrium, so that's all we have to do. So I have minus shear. Now, shear has a lever arm called x, plus the moment, about a moment as a function of x, and that's going to be equal to 0. So I can solve this for the moment is equal to 2.5 x. That's kilonewton meters. All right, so there we have an equation that defines the shear, which is just a constant, and an equation that defines the moment, which is not a constant. It is actually a function. All right, how about between B and C? So this is between A to B. Between B and C, we draw another little section. So I'm going to draw it right here. And we're going to draw the section. It's going to be a little bit longer. We have to keep starting at our reference point of A. But here I'm going to include that 5 kilonewton downward force. I still have positive shear and positive moment. I have a new x value. All right, let's see if we can find out the shear moment equations that are defined between B and C. Sum of the forces in the y is equal to 0. So I have AY minus 5 minus shear is equal to 0. So here it says that shear is equal to negative 2.5 kilonewtons. All right, how about the moment? Sum of the moments about A is equal to 0. So in this case, I have minus 5 times the lever arm of 2 minus shear times the lever arm of x plus the moment is equal to 0. Again, shear is equal to negative 2.5. So in this case, it's a double negative. So that's plus 2.5x plus the moment is equal to 0. And then setting this equal to the moment, you get moment is equal to 10 minus 2.5x kilonewton meters. Anyway, there's our moment equation. Here I have a fixed support with a couple and a 100-pound load at the end. The way to get started is find the reactions. Let's draw the reactions on the picture. I know there's an AY, an AX, and a moment about A. All right, let's sum of the forces in the Y. Sum of the forces in the Y is equal to 0, so I have minus 100 plus AY is equal to 0, so AY is equal to 100 pounds. Sum of the moments about A is equal to 0. All right, what have I got? I got a reaction at A minus the 800-pound couple minus 100 times the lever arm of 10 is equal to 0. So we have the reaction at A is equal to 1,800 pound-feet. All right, so those are the two reactions that we would take to the next step. If we want to find out, now there is a discontinuity here. It's not a shear discontinuity, but it is a moment discontinuity. So let's write the shear and moment equations that happen between A and B. Let's just see what they look like. All right, let's draw a section. And I'm going to draw a free body diagram of that section. I have an AY and a moment about A. Got positive shear, positive moment. So let's sum the forces in the Y is equal to 0 and see what we get. So I have AY minus shear is equal to 0. So shear here is equal to 100 pounds. Sum of the moments about A is equal to 0. So again, I'm just talking about this section. This is a moment about A. I have MA, which I've solved for. This is distance x minus shear times x plus m, which is a function of x, is equal to 0. So let's put our numbers in here. I have positive 1,800 moment about A. Shear is 100 times x plus the moment as a function. So I got moment is equal to then negative 1,800 plus 100x pound-feet. Okay, that's the shear and moment between A and B. So I should put here A to B. Well, how about from B to C? Let's go ahead and write or draw a little section here. We're going to do a similar thing. I'm going to draw a little free body diagram of that section. I have an AY and a moment about A. I'm going to have an applied moment here, that applied couple, but then I'm going to have that positive shear, positive moment. Let me fix that a little bit. Positive shear, positive moment. This is at a distance x like that. Scooch this up just a little bit. Okay, let's sum the forces in the y. Sum of the forces in the y is equal to 0, so I got AY minus shear is equal to 0. So shear here is still 100 pounds. Sum of the moments about A is equal to 0. So I got moment about A minus 800, because that's going in the negative direction, minus shear as a function of x, or as a multiplied by x, plus the moment as a function of x is equal to 0. And here I have m. Let me move that up a little bit. We have moment here is equal to negative 1,000 minus or plus 100x. Okay, let's graph these things. We're going to graph the shear, and we're going to go all the way from. Let me zoom out a little bit so you can see the whole problem. It says that between A and B, shear is, here we go, shear is 100, and then between B and C, shear is 100. So clearly, shear doesn't change. So let's go ahead and draw it there. I'll say that it is constant all the way across at 100. Okay, let's go ahead and look at the moment graph here. So what we're going to do is find out what it is between A and B, and then from B to C. So let's look here at x. Here's our equation. At x is equal to 0, moment is equal to negative 1800. Let's go ahead and put that in there. So I'll say the moment graph starts at negative 1800. Now let's look at x equals 5. X equals 5 is right here. So if you put 5 in here, I have negative 1800 plus 500, so that'd be negative 1300. It looks like that is a straight line, so this is negative 1300 from here. This is an equation of a straight line, so it's pretty easy to see. All right, let's move from B to C. Here is our equation. So at x is equal to 5, moment is equal to negative 500. So negative 100 or negative 1,000 plus 500, so it'll be negative 500. And then at x is equal to 10, I have moment is equal to 0. So that's going to be out here. And again, this is a straight line. You can see that's an equation of a straight line. So here's a picture of our moment graph. Then you say, what happens between at x equals 5 here between 1300 and 500? Well, this is one of our discontinuities that I was just talking about. Whenever there's an applied moment, it has an undefined spot right there. So on one side of the equation, or one side of that point, you'll have one value. On the other side, you'll have a different value. But right at that point, you kind of have two values, and it's undefined, if you will. So we call that a discontinuity. But anyway, that's the shape of the moment graph.